system programs on the Linux operating system today that makes use of things such as Python, shell scripts, and those things that really are just a very high-level abstraction of what happens underneath the scenes. We did talk about how you can run an operating system compiled for one architecture to run on a different architecture. Now let's just see quickly, what do you understand on the word architecture? If I talk about these things, but I'm not so sure you can understand. What do you think is No, not design. No, it's not. No, it's not. Give me an example. Then I'm talking about what processor it's built for. For instance, if you say that I'm developing an operating system that can run on the x86 architecture, then it's for that specific processor. Or the ARM processor is a different type of architecture. Or the RISC-V is a different type of architecture. So in context of an operating system, the way when you install it, when you implement it, when you can run an operating system compiled for one architecture, if you want to run it on a different architecture, in that context, it's the processor that we're talking about. Okay, so there's a difference. You cannot just take the Windows operating system and install it on a for instance, on your cell phone. It doesn't work. You cannot do that. You have to potentially recompile it so that it can run on your cell phone. Because your cell phone has a different architecture than your PC. Okay, so please get these terminologies and stuff right in your head, depending obviously on the type of questions that we're talking about and what context you're talking about. So you were correct, those talking about the architecture. Is it modular? Is it built with different? That is also an architectural approach. That is correct. But I was specifically looking for what type of processor we were running on. Okay, so let's talk a little bit about some of the approaches mentioned in the textbook around what you can expect operating systems to be built on. So there's structures. And we'll look at a very simple structure. In fact, it's very haphazard structure, which was typically the example of MS-DOS. We'll quickly talk about a little bit more of a complex structure, which was the Unix operating system. And then we'll talk about, before we actually get after Unix, we'll talk about layered approaches. Then we'll talk about microkernel approaches. And then in between there somewhere, there's also a modular, what they call loadable module approach. So let's first figure out what's happening with the MS-DOS operating system. Now with MS-DOS, the operating system structure was actually not that difficult because you had your application program that ran here on top, and in many cases the application program directly went to what they call the ROM BIOS. Who knows what a BIOS is? Yes. Yeah, and what does ROM mean in that context? Read-only memory. So it's basically on the motherboard there's a chip with a number of code built into the chip that you could use. For instance, if you wanted to output something to the screen, you didn't know how the screen card worked. You could just call, I think it was interrupt 13 for instance, posted a few registers and poof, out popped a little character on the screen. That was given to you. So a lot of that code was inside the BIOS and the ROM of the PC itself. And your application programs just called them directly. Obviously, when things like sound cards came out, like the Sound Blaster card and this card that you plugged in, those became a little bit more complicated, and you had to load special device drivers then that sat on this layer. Called it MS-DOS device drivers, and then your application called those device drivers instead of the ROM device drivers, and they then did the necessary communicating with the ROM BIOS and so on and so on. So it was really like crazy dear Macari. It didn't work well, and when an application crashed or froze, the whole machine basically crashed and froze. This obviously operating system didn't support multi-applications, so you could only run one application at a time. So you ran it, finished, reboot the machine, load your new application, finished, reboot the machine, and so on and so on. Okay. It had this principle of a terminate and stay resident programs, which was this layer, but it was rarely used by the applications on top. For instance, you could, for instance, install an antivirus program and kind of stayed in the memory of the program of the computer that looked at what the application was doing to ensure that you didn't accidentally got infected and things like that. But very, very limited capability. The Unix structure was the first real operating system that you could, for instance, run, but obviously on very big machines, but it had a bit more of a structured approach, and it had these principal aspects of layers, but it was also a little bit dear Macari here in the middle, a little bit not great here in this section, which was effectively the kernel. So the layers that the Unix operating system definitely identified was that the user applications was sitting at the top of the operating system, so this was the users. They then activated or interfaced with the shells and the commands and the compilers and the interpreters and certain system libraries, and they then did the whole system call. Remember system calls? We talked about that yesterday. They did the system calls into the kernel of the operating system, and in the kernel of the operating system you had this big monolithic piece of software code running that handled device drivers, I/O, everything, well, virtual memory, CPU scheduling, all of that intelligence was in this big piece of software in the middle. If you, for instance, took the operating system, Unix operating system, and you wanted to install it, or if you wanted to add hardware to that machine, you had to recompile the kernel so that it could run on that system. That was the only way that you could get that new device from working. So basically you rebuilt the operating system every time you added new hardware. It wasn't ideal, but that's the way that it worked. And you'll see later on that that principle of doing it changed slightly, making it a bit easier. And obviously, this kernel operating system interfaced with the hardware directly, like with different controllers, device controllers, memory controllers, and etc. etc. So that's another way, and really what the textbook just wanted to show you is the big difference between your typical MS-DOS structure and the way that Unix is. You'll see later on, we'll talk about different approaches, and this one used a layered approach, but it still had a very monolithic structure, as I said, in the middle. The word monolithic, just see if you can remember that, it means one big structure. Okay, one big thing, it's a unit, and it basically handled everything inside this one big unit. That was what the kernel was in the Unix operating system. Later on, the system designers, well, not later on, but there's a definite approach to trying to separate the operating system into what they call layers. Now, the operating system might be divided into a number of these layers with the principle that each is built on top of the lower layers. The bottom layer, which is typically called layer 0, is the hardware, and the highest layer is the user interface. And then you could have multiple layers in between, with one layer basically talking to the layer below it, that layer talking to the layer below it, eventually getting to the middle layer at the end of the day. There's not that many operating systems that follow this specific type of design, but there are elements of these type of design in your modern operating systems. I mean, just by you looking at the Unix operating system with the users running on top, they talking to shells, etc., basically systems and libraries, and then they talking to the kernel, and then they talking to the hardware. It's the idea of layers is in here. Hopefully you can see that. And this layered design was also initially taken into consideration when IBM, well, that stage Intel, but basically when the Intel processors were originally developed. From the 386 onwards, when they started building in what they call protected mode, that's when they started building in these layered access in the actual chip. Ring 0, ring 1, ring 2, ring 3, etc., etc. Although their ring 0 isn't exactly the hardware layer. Ring 0 is the layer that could access the hardware. Okay, the disadvantage of building an operating system with too many layers is that you can slow down the running of the operating system, because every time you want to do something with hardware, it has to flow through all of these layers before it eventually gets to the hardware, and the hardware message has to flow all the way up these layers as well. So it's not an ideal design if you want to make it fast. For instance, let me tell you a little bit of a story. When Microsoft first developed the NT operating system, now that was in the middle or the early 90s, late 80s. Now, the only other operating systems that they had at that point, well, the other operating systems that they had was MS-DOS and Windows 3.1 and 3.0 and so on. Now, the Windows operating system was a 16-bit operating system, and obviously MS-DOS was an 8-bit operating system, so it wasn't really great at all. So they developed the NT operating system to run on different architectures. Okay, hear the word. So DEC Alpha was one of the processors that could run on, and Intel new 32-bit protected mode, and a few others as well. They really developed the operating system into quite a few of these layers. Now, they moved a lot of these screen and updating components out of the kernel into what they call a higher level, which typically ran in user mode. That caused the operating system to be a very bad candidate to run your games on, because your games typically had to update the screens quite often. I mean, when you first-person shooter and those things. So the code really ran from the application into the graphical graphical libraries that basically ran in user mode, and that then eventually flowed back into the kernel mode, and then into the hardware and back up again, all of those levels, and that slowed the machine down. However, it made the operating system very stable, because you could have something happening in your graphical device drivers, and it did not affect the rest of the operating system. But it came with a price. So that's why eventually Microsoft moved many of these components very much like we saw in the Unix operating system, into this middle layer to run in kind of like a modular kernel environment. That sped up the operating system significantly, but made it a little bit less stable. And we'll talk about that in a few minutes, see why that was the case. And this is actually where we're going to start talking about. So there's another approach, which they call the microkernel approach. Now, the microkernel approach says that when we look at this monolithic structure that you see here, I mean, the file systems are in here, the device drivers are in here, everything that has to do with both those components, it's quite big, they all run in the kernel of the operating system. The problem, however, is in many of the cases, that code isn't controlled by your operating system developers. For instance, let's assume NVIDIA brings out a new graphics card. For you to talk with that graphics card, you have to install what they call a device driver. Okay? Remember that. So the device driver is written by NVIDIA, not Microsoft, not Unix, not Linux, nobody like that. They are developed by this other company. There's no way for Microsoft, or there's no easy way for Microsoft to actually control what that code does in that device driver. Is it responsible code? How does it handle the execution of things, etc., etc.? When that code moves into the kernel, and let's say, for instance, that code misbehaves, which is very likely. I mean, there's bugs and stuff happening in code all the time. It effectively can crash the whole operating system. So if something goes wrong in the kernel, that big modular area in the middle, it affects the whole computer. But if something crashes in user mode, if you write an application today, a C++ application today, and that application accesses memory not allocated to it, it doesn't crash your whole operating system. It doesn't stop the operating system from responding. It only crashes that application. So meaning the rest of the running applications, they are safe. You might have seen I think in the old days they called it the blue screen of death on Windows. These days, I don't know what they call it, but it's also effectively a blue screen. When that thing happens, it means something went wrong in the kernel of the operating system. Now, it's not always the code that's the problem there, it can sometimes be the actual hardware that's the problem as well. But there's some interface there that's not great. But that causes effectively something to go wrong in that middle section. And that is what microservices tries to minimize or mitigate. They move a lot of the actual code that used to be in the kernel, they move that into user space. To say that, listen, if something goes wrong in a device driver, that's cool. Only the device driver fails. The rest of the operating system keeps running. If, for instance, you want to access the NTFS file system, who knows what that is? NTFS file system. Sorry, yeah. You wanted to say? Yes, you wanted to say something? You know NTFS?
Isn't it the format of the Windows hard drive?
It's the format that the Windows uses to store its files. Who knows what file system? Sorry, yeah?
No. Realizing.
Okay. Who knows what file system Linux uses by default? Yeah, it is a. Sorry? It's what? Either ext4 or like there's another version. No, not ext. EXFAT is an extension to the old FAT file system that Microsoft had. It's definitely not what Linux uses. Linux support. Well, let me put it this way. So what I'm trying to highlight is that there are many file systems out there, meaning ways in which we can store files on hard disks. And for instance, your Windows operating system by default supports about 4 or 5 of them. NTFS, FAT, FAT32, CDFS, there's a few others as well. So they're all different ways. And that file system code, the thing that understands how that file system code works, If it, for instance, lives in the kernel of the operating system and something goes wrong with that code, then there's a problem. Unix, for instance, of Linux is well known for its ability to adapt so that you can install different types of system, that you can store it on different types of systems, which means it's quite good at adapting new file systems as well. The same principle holds true. If, for instance, you are a developer and you are developing a new file system, you can kind of hook it into Linux, but where do you hook it into? In the kernel or in user mode? Microservices says, for instance, those components lives in user mode so that when it misbehaves, it does not affect the whole operating system. That's the advantage of that type of design. There's a lot of, so in general, when a typical operating system service, such as a file system that needs to communicate with the device driver, because they have to, you have to say, I want to go fetch this file from that cylinder. Both the device driver and the file system lives in user mode. Processes by default living in user mode are isolated from each other. They can't talk to each other normally. So the way that it's done is through message passing. You'll see now in the slide that's coming up that messages are sent from the user mode component into the kernel through the message passing architecture or component back up again. So it's a context switch from user into kernel back into user mode by sending these messages, and that's the way they do it. So there's a bit of a, again, disadvantage in that it slows down your typical communication in your operating system. And this is what's mentioned there at the bottom. There is a performance overhead of user space to kernel space communication, because this continues back from user to kernel back into user, and so on and so on and so on. However, the benefits are the following. It's easier to extend the microkernel, because you'll see that they are very, very, so micro means small, eh? Small little components that lives in the kernel of the operating system. It's easier to port the operating system to a new architecture, because it's really, a lot of the code that you have is in user mode. It's easier to port those things to a new architecture than taking something that's in kernel mode and then recompiling that, because that's the thing that has to communicate with the hardware. Stuff on top of that doesn't have to communicate with the hardware. It's not that dependent on the architecture, the processor that you're running on. Okay, so remember the word architecture. It's a lot more reliable. Something goes wrong in user mode, doesn't crash the whole operating system. The chances that, because there's a lot less code running in the kernel, it's easier to check the total amount of code in your microkernel modules for bugs than it is, for instance, in a monolithic structure. You know, I talk about a lot less, it's like in the magnitude of 100 times smaller than your typical monolithic structures. It's a very, very, very small, purpose-built modules in the kernel. And in general, it's a lot more secure, because everything running, or anything running in kernel mode, has access to everything else. The big problem that Microsoft is currently working on with some of the hardware that new computers are shipping with is to try and mitigate a potential problem where malware can install itself as part of the operating system, meaning as part of the kernel. Because if malware can run in your kernel of the operating system, then it effectively has free reign over everything that you can do. And it's really hard to detect that. So what they try to do now with the whole trusted platform modules and virtualization is to kind of move the kernel of the operating system into this virtual machine and keep it protected. And nothing else can basically access that without having to go through the necessary components and access. Okay, so it is available currently in Windows, well, both Windows 10 and 11. If you have the necessary hardware to support that, you can actually do that whole movement away. Very, very useful on server environments where you typically have these things running for a long time.
It's the sandbox.
Yeah, I don't know if that's the formal name for it. Microsoft has probably a different name, but effectively it tries to put let's call it the trusted components of the operating system into a virtual machine. Just keep everything else away. You don't have access let's call it third-party developers that develops like device drivers, they don't have access to that either. So here's a little picture of typically what you can expect from microkernel systems. You have these microkernel components, very, very small, typically only a few components such as your interprocess communication. You'll learn in the next chapter that interprocess communication is a vital component so that processes can talk to each other. We'll learn all about mail slots and name pipes and shared memory and those things. You'll learn later on that memory management is an absolutely core component of the operating system so that it can basically virtualize memory for your computer. So that if your computer doesn't have enough memory, some of the memory that you need can be offloaded to the hard disk and then later on loaded back in again. That's all kernel components. And obviously, CPU scheduling is probably the most important thing running on your CPU if you have multi-user or multi-user systems to ensure that and multi-processing systems so that each process can get a time slice. It's a very, very low-level component that controls who has access to the CPU. All right, and as you can see, when we have messages being passed, let's say from the file system that wants to read something from a disk, it has to go via this message passing mechanisms through the kernel to the device drivers. They then eventually get stuck via there's another component which is the basic I/O, goes to the basic I/O components, they then get it off the hardware, sending it to the basic I/O, they then send it back to the device, and that then flows all the way back to the file system, which eventually flows all the way back into the application program so that you can actually see it. It's quite a long road, and that's what makes microkernel approaches not that popular, because of that overhead that you basically have. There's another approach. Remember we said that this monolithic structure inside Unix, it's really, really big. Every time a new device added has to recompile the whole kernel. So what they thought about was saying, why must we recompile everything? Can't we create these modules and then use the module and load it into memory as I need it? And that's the way in which both Microsoft Windows as well as modern Linux and Unix actually work. No need for recompiling the kernel. You basically have these loadable modules, and as you need it, they will be loaded into the memory of the computer and it makes use of it. Where in the memory? Well, it depends. If it's a kernel component, like a file system component, it still loads it into the kernel. So you still have that disadvantage that if it misbehaves, well, the operating system will crash, but at least there's no more, everything must be loaded into the kernel. You only load it when you need it. It uses the principles of object-oriented approach. Each core component is separate. Each talk to the others over known interfaces, so really just function calls effectively, and each is loadable as needed. Overall similar layers, but more flexible that we have these days in Linux and Solaris systems. And here's some of the module types that you can get in the Solaris operating systems. So Solaris is just a general operating system name that you can get on the Unix environments. So your different file systems, system calls, so what is interesting there is you even have loadable system calls. So your system calls can actually fluctuate as you need them. Different types of formats be executable, the streams, modules, and select others, they're basically loaded in as necessary. So now we've learned that operating system designs can follow different approaches. You have a layered approach, you have a microkernel approach, and you've got this modular approach, so that you basically load this stuff in. Modern systems really use a mixture of these things, and you've kind of saw it already in Unix. So I'm just going to quickly go through some of the type of modern operating system that we have today, and show you how they typically look like, and draw it in an architectural structure. It's called hybrid. Linux and Solaris kernels in the kernel of kernel address space. So again, they call it monolithic. But plus it's modular for dynamic loading of functionality. So that basically just means that whenever we load stuff into the kernel of the operating system, it's still in the kernel, but you only load it when necessary. Okay, so that's what it's meant there. Windows are mostly monolithic plus microkernel, so they've got different kernel components there for different subsystem personalities. Apple Mac OS X is definitely hybrid. They use this layer upload, which is the user interface, plus Cocoa, it's called, which is like your programming interfaces. It's your libraries that's basically exposed to the developers so that they can write Mac OS X applications. Below that, in the kernel, you actually have two types of kernels. That's quite interesting. The Mac microkernel, which is this thing there. We've seen it here as well. There. They just mentioned here Mac OS X kernel. The Daron was partly based on Mac, MACH. So one of the core components in the OS X is this Mac microkernel, but it also consists of the BSD Unix part. So BSD was an open source operating system, and they've modified it specifically for the Mac OS X. This is the kind of what you can see how it looks like and how they each fit in. So at the bottom, you've got this Mac environment, which is your microkernel components, and then you've got a BSD monolithic kernel running in there as well. Each of them, well, inside your application development environment, you've got like your Java runtimes, your Cocoa libraries, your QuickTime, and your BSD libraries that is then exposed to applications running in your user interface, called Aqua, that's what it's called. Right, so that's kind of what you will see, or the picture that we get in OS X. In iOS, as an example, uses a mixture of what you had with Mac OS X. In fact, the developers of Apple decided that they didn't want to go and reinvent the whole iOS. So they basically took the Mac OS X and they stripped away a lot of the complicated access there and made it very, very small, and they ended up with this kind of principle. So they still had the core OS, which consisted of the BSD and the Mac components of the BSD and Mac. On top of that, you had certain core services running. On top of that, you had media services, and then they had a special version of Cocoa, I can't pronounce it properly, but it was written specifically for touch screens. That was handling that. Android operating systems. They are developed by the Open Handset Alliance, which means it's open source. That's the big advantage that Android has over your iOS. It's also the reason, potentially, why it's maybe not as trusted as iOS. Yes? Mac OS X. Yeah, so the BSD component, yes. Well, they control the source. So no developer can modify OS X's kernel. That's the thing. Where in Linux, you can modify the Linux kernel the way that you feel. Right. So the same with Android. It's potentially open for everybody to change the kernel. So let's say, for instance, I build a new cell phone today. I can potentially take the Android operating system source code and I can change the code in there so that it can run on top of my handset. That's the big advantage that but I have to obviously just work with the Open Handset Alliance to make sure that it gets put into the mainstream of the operating system itself. In terms of the layers, it's very similar to iOS, believe it or not. It also has these multiple layers, but you'll see that they use it for different purposes in different layers. In the very lowest level, it's based on the Linux kernel. But again, it's modified Linux kernel. and that makes it kind of easy to basically get used to, and it's fairly available, and everybody can have a look at it. It provides process memory and device driver management, it adds power management components. Then on top of that you have what they call the runtime environments. So most of your Android application obviously gets built on top of basically Java applications, but there's a special version of Java that they run inside here. And there was a big fight that, who owns Java? It's Oracle, I think. Sorry? It's Oracle. Oracle had with Google because the problem was historically you needed a license to ship your Java runtime environment. So that you could, so let's say for instance, I write a Java application. If you want that Java application to run your operating system, it's fine, go build a Java runtime environment, but then pay Oracle a license for that Java runtime environment that you built. Google didn't do it. They basically built their own Java runtime environment called the Dalvik VM. And, Java basically, or Oracle said, no, hold on, this is still our proprietary information that you have. For every handset that you ship, you have to pay us a license. And then there was obviously, no, they don't want to because it would have cost them a lot of money, which I don't think they had to pay a license. Probably something was settled outside the court. Who knows? I can't remember the whole story. Anyway, there's a number of other libraries that helps you to develop things for your web browser. That's called WebKit. It's got a built-in database. It's got like SQLite built in. A lot of multimedia support and a much smaller C library that's available. So if you want to draw it, it's kind of how it looks like. At the bottom we've got our Linux kernel. The Android runtime is our Dalvik virtual machine. That was the special version of the Java runtime environment that they had. On the left-hand side, a number of libraries are exposed to the applications so that you can easily write these applications, very similar to the Apple ones, SQLite, OpenGL, WebKit, and those things. So whenever you write your mobile apps on Android, you're actually making use of a lot of those libraries that you see there. And obviously, they all go through the application framework layers. Your applications are sitting there on top. Before we end up this chapter, let's just quickly recap what happens when you run your operating system. So when you switch on your computer, then how does that computer run the operating system basically? So when you switch it on, what needs to happen is typically there's some kind of firmware component that needs to start. Now that firmware component historically was in the BIOS of the operating system. These days it's called UEFI, U-E-I-F-E. That's the acronym for it. Unified Extensible Firmware Interface or something weird like that. But effectively what that does is it loads a very basic program from that hardware into the memory of the computer. The computer then starts executing the code in there, and all that code really does is it gives the basic knowledge on how to read from the hard disk. So it basically goes to sector 0 on the hard disk, and it starts reading your first the first piece of code, which is typically what they call a bootstrap loader that's on there. So on Linux, that bootstrap loader is called Grub, G-R-U-B, and that then starts up and it then allows you to select what operating system you want to further run. So you can, for instance, on Linux very easily install multiple versions of the Linux operating system and even Windows. And then the first thing that you will find is when you switch on the power, it will ask you which operating system do you want to run. I want to run Linux, Red Hat, I want to run SUSE Linux, or Windows. And then depending on what then happens, that loader then starts running the boot loading code of that specific operating system from the hard drive. It is possible for Microsoft to have that menu as well, but it's not so much a Grub loader, but they also have an operating system loader, but it's a little bit more tricky to get that working and displaying in your machine. So what a lot of people do is they just install Linux, and then they install Windows after that, which still keeps the grub loader running. Yeah, so your initial piece of code, that's called the bootstrap loader, that's stored in the ROM or the EEPROM, locates the kernel and loads it into memory, but it doesn't have to always load the kernel. It can also load what they call a bootstrap loader, which then loads the kernel of the system, which is this two-step process that they are talking about here. Okay, right, so that's the only thing that you need to understand extra in this chapter. This brings us to the end of this chapter. So it's time for us to quickly take 10 minutes and then we'll start with the next